All right, today you're going to get more practice with determining whether a molecule is polar or not based upon the structure and the difference in electronegativity. So this is the worksheet you're going to be working with. Formulas for the molecules you're going to be using are here. You can either do this by building the molecules or by using the online interactive that I have available. So here we have, this is just the worksheet that you have. This is an app that you can use. Now when it opens, it might already have the one that I brought up on it. So H2O2. So here's the structure over here. In order to get this to come up, all you got to do is type up here H2O2 exactly like what I have. Oh, no, that did not work at all. Let's try that again. H2O2. I think I put a 0. That's why. All right, so don't put a 0 instead of a, oh no, oh, that definitely won't work. Okay, so you're going to look at the structure, and based upon this, I need to decide if it would be polar. I also need to consider the electronegativity of the molecules. So this is what my shape's going to look like, and I want you to keep that in mind. But when you punch in your equations, you're just going to put them up here, and you can move them in three-dimensional view. The one thing I want to point out with this is that if you spin it, your hydrogens, which are the white ones, are on the top, and your oxygens are on the bottom, so you definitely have a difference in where those are positioned. Okay, so now we're going to look at the actual molecular model. If I build it, it's going to look like this. I've got my 2 red oxygens attached to my 2 hydrogens. Again, you can tell your hydrogens are above the oxygens, so we will have a difference in electronegativity and potentially a charge. So I'm going to go ahead and I'm going to draw this on here. So I'm going to have your H, your O, and another H. So just kind of show that they're staggered so that one side is the H's, the other side is the O's. The electronegativity value with the greatest difference. I'm going to point this out, like we'll explain in class. So right now we're looking at the fact that this has a difference of an O and an H. So let's look at, we're basically looking at the comparison of the OH bond. So if I bring my table with the electronegativities on it, my O is 3.44. My H is 2.20. And if I subtract those, I'm going to get 1.24. That alone tells me that it should potentially be polar because it's between the 0.5 and the 1.7. However, I also have to consider the shape. Now, since this shape has the H's on one end and the O's on the other, then I am going to say this is going to be polar. And why? Because the electronegativity, the change in E, equals 1.24, and H's and O's have opposite sides. Okay. Now, if we get into a larger molecule, like so, okay, now with this one, this would be CH3CH2OH, okay? And I'll go through each of these molecules as well in a different video. So if I have this molecule, first of all, my carbon is essentially stuck in the middle here, and it's stuck in the middle here. The only ones that are really standing out, the hydrogens are all on the outside. And then I've got my oxygen. My oxygen is accessible. So for this one, I'm really going to be looking at my difference between the O and the H again, because my carbons are both stuck in the middle. When you're trying to determine the electronegativities with the greatest difference in value, since the carbons are not going to impact the polarity of this molecule, I'm looking at just the oxygen and just the hydrogen, because those are going to have the biggest impact on the polarity. So we've got the oxygen sticking out here. We have hydrogens everywhere else. So as long as there's a difference in the electronegativity between this and basically the rest of the molecule, then I can say it's polar.